So I'm Pierre, and I will present joint work with Patricia about GADTs, and this is part of an ongoing project about finding initial algebra semantics for GADTs. That's not a problem if you don't know what it is, because that won't focus on that. But the first part of this project is to understand how functional are those GADTs. I will detail what they are. And so for that, we need to talk about what it is to map over data structure in those kind of data structures. So I will divide the talk in three parts. So the first part will be about defining what are generalized algebraic data types, so these GADTs, and how they compare to more usual types that you are used to, namely ADTs, so algebraic data types, and nested types, which are a middle ground between the two. Then I will try to convey some intuition about what it is to map over data structures in the context of ADTs and nested types, so the mapping that we are used to. And then I will explain how we can generalize that over GADTs and how it gets us to a set of constraints. So let's first talk about what are those data types. So you might already know what are algebraic data types, but if you don't know, they are just families of inductive types, which means that I fix an index alpha, for example, like in that data type list, I fix an index alpha, and once this alpha is fixed, I'm defining a usual inductive type. So in the case of list, there is this nil operator, which is constructing the empty list, and then there is this double colon operator, which takes a label and a list and makes a new list by just grafting the label on top of the list. Another ADT that you might be familiar with is binary trees, where there is the empty binary tree. And then if I have a label of that alpha and a left child and a right child, which are both binary trees of alphas, then I make a new binary tree of alphas. And so those two examples are of arity 1. There is only one alpha in parameters, but of course, we can do that with multiple parameters, including 0 parameters, and then we just find the usual inductive types. So for example, n, where we have a constructor 0 and a constructor sucks that take a natural number and give you the successor of this natural number. And I want to draw your attention to the fact that once we have fixed the parameters, so alpha in the case of list and binary tree, then the rest of the definition is just a usual inductive type with that alpha in the context. And I draw your attention to that because if we go to the next step, which are nested type, then we have to change this our mindset about that. So nested type, in comparison, are inductive families of types. So they are not families of inductive types. They are inductive families of type in the sense that we have to define the whole family in one go in an inductive fashion. So one of the most known example is perfect trees, where you have a empty perfect tree for any alpha, so penile, and then if you have a label of type alpha and perfect trees of alpha cross alphas, then you can make a p-tree of alpha. And so the big difference between that example and the previous one is that here, in the argument of p node, the second argument is using perfect trees at an instance which is different than the one currently being defined, which is p-tree of alphas. A second example where we can take advantage of this change of instances, but in a more complicated fashion, is to look at what is called bush, where we also have empty bush for each alpha. And then if I have a label of type alpha and a bush at the instance bush alpha itself, then I can make a new bush of type alpha. So again, this instance here of bush is not alpha itself. It's a different instance, and in that case, it involves the type which are being defined, the type family which is being defined, being bush here. Okay, so we see that those nested types are already more hairy than the usual ADTs, but we can go even further, and that is what we call GADTs, or generalized algebraic data types. So they also are inductive families of types in the sense that we have to define the whole family in one go, but on top of that, we kind of break the uniformity of the family by putting constraint on the return type of the constructor. So for example, here is a GADT that you could have if you try to encode some kind of type calculus in in your ambient language. And yeah, by the way, I didn't say it, but for all my example, I would use AGDA just for expository purposes, but you can do the same in most functional programming languages like Haskell or Camel. Just the syntax is changing, but not the actual content. Okay, so this GADT, for example, you see as a first constructor nat, which takes a natural number and returns terms of nat. So here you see that it's not a constructor which returns term of alpha for a generic variable alpha, but we are constraining the return type. Ing, on the contrary, is just something that we could have add in an ADT or an SC type, kind of a normal constructor. But pair, again, is something which is constraining the return type. So we take an element of type term alpha and an element of type terms beta, and we return an element of types terms of alpha cross beta. So the return type is constrained here. And pi1 and pi2 are taking arguments of terms, types terms of alpha cross beta and returns respectively terms alpha and terms beta. And so here also, in a more subtle fashion, the two return types are constrained because this alpha is really just the first projection of this tuple alpha beta, and beta is the second projection. Okay, one other GADT that you might know is the equality GADT, where that time we have two arguments, alpha beta, and the type alpha is equal to beta is supposed to be the witness of equality between alpha and beta. And so there is only one constructor which says that for all alpha, we have an element reflexivity of alpha is equal to alpha. And so again, here, alpha is equal to alpha is constraining the return type because this second alpha is not an arbitrary generic variable beta. It must be the same variable as the first one. Okay, so now that we have established what are the different types that we are looking at, we are going to go to what is the usual idea of mapping, and then we will explain how we can do that on those type of GADTs. So first, what it is to map usually over data structure in a general sense. So if I give you a list and I tell you, well, you have this list, which really is just written, it's a visual representation of the list written like that with the constructor. If I say, well, keep the structure of this list, but just change the data according to the function p, which sends even number to true and odd number to false, then you will come up with this list. And so how do you do that? You just look at each of the labels in the first list, and you just apply the function p to each of those labels, and you find the second list. If you look at, and the second list is just a visual way to write the actual list, which is in the bottom. If you are a little more systematic about what you are actually doing, you are looking at the first label first. You are applying the function p to this first label, so 3, and then you notice that you have a list for the rest of your structure, and you reapply that recursively. So really, which is at play here is you are applying this function, which takes a list of alpha in input, a function from alpha to beta, and return a list of beta. And is saying, well, if my structure is just the empty list, whatever is the function, I'm returning the empty list. But if I have a head followed by a tail, then I apply the function to the head, and then I use a double count operator with the recursive process on the tail. Okay, so I think most of you know that, but it's good to build some intuition. We can do the same with binary tree. So if I tell you, well, keep the structure of this binary tree, but just change the data according to the same function, and so this binary tree is a visual representation of this term. If I write that with actual constructors, then you will come up with, I guess, this solution, and you do the same. You just look at each of the label, each of the data, and you just apply p to those, and you find the element which has the same structure, but where each of the labels have been replaced by their parity. And so this is just the tree, which is written like that if you want the formal version. And again, what do you do, formally speaking, is you look at the label in the top 3, you replace that with false, and then you said, I have 2 child, the left child, the right child, and I will redo the process on those. So what's happening behind the scene is that you are applying this map function. It was the same as for list. You just put the empty structure to the empty structure, and when you have a graph of a label with left and right child, then you apply the function to the label and you reapply recursively the map on the left and on the right. Okay, so let's move on to nested type, which are a little more complicated. So the same tree as before can be seen as an example of this data type perfect tree that I defined before, where the instance here is alpha cross alpha and not just alpha. So this visual representation is really just this perfect tree. And if I ask you to keep the structure of this perfect tree and map the function p, again, you will probably come up with the correct solution and end up with this one, which is just a visual representation of this term. And basically what you do behind the scene is exactly the same as before, but with one more subtle, there is one subtleties here which were not present before, which is, well, the first case is you map the empty perfect tree to the empty perfect tree. But when you have a p node, then you apply f to the label, and then you want to apply recursively your function to the second argument. But the second argument now is not a p tree of alpha; it's a p tree of alpha cross alpha. So you can't map f over this t. T is a p tree of alpha cross alpha. Mapping f over it doesn't make any sense. You need a function which is of type alpha cross alpha to something, and so you map f cross f over t. F cross f being the function which takes a pair and apply f on both components of the pair. Okay, so we see that nested type are a little more complicated, but we can still follow the same kind of reasoning when we are trying to map. So let's try with bushes. So now this is a visual representation of this bush, which is a little bit complicated, but it's just a bunch of B nodes which are applied together until we reach on each of the branches B nil at some point. And if I ask you to map P, you will have no problem either with the visual representation or with the actual term, and you will come up with this one, which is really just this bush. And so what do you do here? You apply the same process. It's a little more involved again because of the fact that the instance of the second argument is at bush A and not at bush alpha and not at alpha. And this is the map that you are applying. If it's a B nil, then you just return B nil. But if it's a B node of a label and another bush, which is a bush of bush alpha now, so this BB is a bush of bush alpha, then you return the B node of F applied to X, and map bush applied recursively to BB. But what map can we use to map over BB? Well, because it's a bush of bush alpha, we need something which is of the form bush alpha to something, and the only map that we have at our disposal is the function here, which is take any bush and map F over B. So it is a little more involved because the function that we are mapping over the recursive call is not F itself, as with P3, it's something more complicated, but we can still follow the same process as usual in our way of thinking. And the idea is, can we do that with GADTs? And so if I take my GADT of before, this term GADT, and I ask you to do the same as before, but with terms in that data type, what would you come up with? So I have three different terms here. The first one is just pi1 of pair of inch3 and inch1. The second one, pi1 of inch of the pair, 3, 1. And then pi1 of pair of nat3 and nat1. So if I tell you to keep the structure of the following terms, you should have a first question, which is, what is the structure? It was kind of obvious before what was the structure of each of the terms that we had for list, binary trees, P trees, bushes. Here, the term structure is not super clear. And so that's one of the things that we have to explain. And then if I say, well, you keep the structure and you change the data according to the same function as before, the parity function, then you should ask me what data. Again, it's not clear what is the data in such a GADT. And so I can give you the answer for those three terms, and then I will try to explain why it is the case. So in the first case, I just replace the 3 by false and the 1 by false, and I get that first term here, pi1 of pair of inch false. And you can see what is the process intuitively, at least. It's like, well, I have this 3, I just transform that in false, and I'm done. And this one in false, and I'm done. The second term, I follow the same kind of intuition. I just replace my data 3 and 1 by false and false. But for the third one, if I try to follow the same kind of pattern, I'm stuck, because if I want to replace the 3 by false and this 1 by false, well, it doesn't type check, because nat needs to take element in the natural number. So I can't write nat of false. It doesn't make any sense. So what is the answer here? Well, the answer is actually that this function p is not mappable over this term. So that's one of the key differences between GADTs and nested types or ADTs, is that sometimes you have a function which has the correct type, it's n to b, and you are trying to transform something in terms of m, terms of n, into something in terms of b, but you can't apply this function. So you can't map p over that third term. Okay, so the paper described an algorithm to know when a function is mappable, to characterize the functions that are mappable for GADTs. I won't go into the detail of what is this algorithm. I will try just to give you intuition by running the algorithm on some examples and giving you some idea of where are the difficulties. And the first main idea in the algorithm is that when you are mapping a function over a term in a type, we are mapping relative to a specification and not to a data type constructor. So let me explain what we mean by that. Specification is just a word to say type formula in several variables. And so instead of saying that we are mapping relatively to list or relatively to bush as before, now we are mapping relatively to all type formula. So this type formula could be list of binary trees of bush of alpha, for example. So it can be composed. And the algorithm that we designed in the paper take 3 arguments, phi, t, and a couple of functions. And the first argument, this phi, is the specification. So it is a type formula in some type variable. So lambda, alpha, 1, alpha, n, into potentially very difficult type formulas in those variables. The second argument is the term that we are trying to map the functions over. And these terms needs to be in one of the instances of the specification. So we need to have some type AI such that phi of the AI is the type of t. And finally, we need functions that we are trying to map over this term t from AI to bi. And so if the tuple of function is mappable over these t's, and we will end up with a term in phi of the bi. And so what the algorithm is returning is a set of constraints on the functions, on the FIs, so that those functions are mappable over t. So it will tell us if those functions has the correct form to be mappable over the term t. And so if we have just a type constructor t as list or bush or p3, then we can call mappable with a very simple specification, lambda alpha t alpha, when the term t is of type ta for some a, and the tuple of function is just one function which is from a to b. And then if the type constructor is, for example, list or bush, the answer of the algorithm will be a set of constraints which is trivial, because every function is mappable over something in list or something in bush. The only constraint will come when there is an actual GADT at play. Okay, so let me explain why the specification is important. So if I have this term, which, by the way, doesn't involve any GADT, it's just list here, already the specification matters. So if I look at this list of lists, I can look at these elements in 2 ways, either as a list where the data happens to be lists, or as a list of lists where the data happens to be natural numbers. And it makes a huge difference. So if I look at that as just a list where the data happens to be list, but it's incidental, then I can map any function from list n to something else where I apply the function f to each of the lists inside. But if I look at that as a list of lists, then the function that I can map are only the function from n to x or some x, and then I apply the function internally to each, in the inner list. In the inner lists. So it makes a difference if I see the list on the top as a list or as a list of lists. Okay, so let's go back to our GADT and see how we can try to map over this first term, which is our first example. So I have pair of int3 and int1. So pair is this constructor. It expects 2 arguments, and my first argument is int of 3, sorry, and my second argument is int of 1. So if I want to map a function of type n cross n to x1 cross x2 over this term, in the specification, just see this term as being in terms alpha for some alpha. Then I want to be able to recursively apply the map under the constructor pair. So what does it entail? Well, it entails the fact that from f, I want to be able to extract a function from n to x1 and a function from n to x2. So I need my f to be of the form f1 cross f2, with f1 and f2 being from n to x and n to y respectively. And if I want to be able to apply recursively the map under this constructor pair, then I need f1 to be mappable over int3 and f2 to be mappable over int1. But in what specification? Well, the specification is given by the form of the argument of pair. So here it's quite simple because it's only terms alpha and terms beta. So my specification is simple in both cases. Okay, and now I continue my my recursive calls. I need to see if asking for f1 to be mappable over int3 entails more constraints or not. Well, it happened that if I look at the constructor int, then mapping something under the int is trivial because we just end up with a variable. So here we don't have any constraint which is appearing. The same for f2 being mappable over int1 is just meaning, well, can I apply f2 to 1? And so we don't have any further constraint on f1 and f2. So the only constraint that we have is the one which is appearing here in the first step. And so the conclusion of the algorithm is that the function of the form f1 cross f2, and only those ones, with f1 going from n to x and f2 going from n to y, are mappable over the term pair of int3 and int1 in the specification lambda alpha to terms alpha. Another way to read that result of the algorithm is to say that we have this structure for the term. So I put boxes in place of the actual data, and this gives me the structure of the term. And so mapping is keeping this structure and only changing the data, which is the one that we input in those boxes. Okay, so this, for example, is fairly simple. There is only one constraint appearing, but it can be more complicated. And now I want to go to the example that I gave you in the beginning of this third section. So the first one was this one, pi1 of pair of int3 and int1. So it's the same term as before, but with a pi1 applied to it. So if I ask, is f from n to x mappable in the specification lambda alpha terms alpha, what does it entail? Well, I see in the definition of pi1 that to be able to apply recursively the map from my f from n to x, I need to be able to have a pair of functions from which the first component is f. So another way to say that is I need a second function, g from n to y, and what is the recursive call telling me that the tuple f comma g should be mappable over whatever is the argument of pi1, which is here, pair of int3, int1. So f comma g should be mappable over pair of int3, int1, but in the specification given to me by the form of the argument of pi1, which is here. So this is my specification. And so here I want to highlight the fact that even if I consider this term pair of int3 and int1 before, what I found about it is completely useless here because it was not in the same specification. So I cannot rely on what I had on my previous slide to do something here more rapidly. I need to do it again, if you want, but with this specification. So continuing from there, what do we need for this fg to be mappable over a pair of int3, int1 in that specification, where we look at the way pair is behaving, and we need f to be mappable over the first argument in 3 in the specification given by this form here, so terms alpha, and we will also need g to be mappable over int1 in the same specification. But let's first treat what this f we will have as a constraint resulting from this bullet point. Well, we already did the job, but we need to do it again. So for f to be mappable over int3 in the specification lambda alpha times alpha, we need to look at what is the argument of int. It's just a variable. And so we need f to be mappable over 3 in the specification lambda alpha to alpha, which we already said doesn't imply any constraint. So it's always possible, no further constraint on f. Now I do the same job with g, and we can do exactly the same, something similar than for f, and so we just end up with g not having any constraint either. Okay, and so what does it tell us? It tells us that in the end, every function f is mappable over the term pi1 of pair of int3 and int1 in that specification, because in the end, we didn't have any constraint resulting on f of this algorithm. So sometimes every function are mappable over a given term. It will not be the same for the, oh, sorry, yeah, I wanted to highlight as before that you can see this result just as saying like, well, this is the structure of my term. And so if I want to keep the structure and only change the data, well, that's what I'm doing. Like, so here the data are 3 and 1, but if I want to change the data according to a certain function, I apply the function to 3 and to 1, and I'm done. The situation change if we change int by nat. So you see here now it's nat. That's what I was explaining before. Nat of something else that the natural number doesn't make any sense. Can we see that emerge naturally in the algorithm? So yes. So we just do the same as before. We say, what does it entails for f to be mappable over this term in the specification lambda alpha goes to term alpha. And then we have the same first step, which is, well, we need some g such that fg, the couple, the pair fg, is mappable over the argument of pi1, so pair of nat3, nat1, in the specification lambda alpha beta goes to terms of alpha cross beta. But now things change because we need f to be mappable over nat3 in the specification lambda alpha goes to term alpha. What does that entail? Well, we can't map anything over something which is of the form nat3, except, or nat any other natural number, except the identity on n, because nats can only accept natural numbers. So we need f to be the identity on natural numbers. And of course, there is no further constraint on f because it's already quite constraining, right? And then we do the same job on g. And so we need g to be mappable over nat1, and that entails that g needs to be the identity on the natural numbers. And we stop there. And so in the end, only the identity is mappable because we just collect the constraint on f, and we see that this is the only constraint that we have. So only the identity is mappable in the specification lambda alpha goes to terms alpha over these terms pi1 of pair of nat3 and nat1. So how can we understand that from the structure preserving but data changing point of view? Well, the structure here of the term is really the following. So 3 and 1 were just like a shortcut for something which can be written with the constructor of the data type n. And so here the whole term is actually only structure. There is no data in that term. In that term, pi1 of pair nat3, nat1, everything is structure. There is actually no data. So everything is part of the structure, and the boxes that are left can only be filled by the empty vector because those are operators of arity 0. 0 is of arity 0, and n itself is of arity 0. So the whole term is only comprises. Sorry, the whole term only comprises structure and no data at all. So when we are keeping the structure but changing the data, we do nothing basically. Okay, so I went over a few examples. I didn't present the whole algorithms, and there is more at play there. And so what I swept under the rug is that the constraints are not linearly discovered. So we can have like more involved example where we can find multiple constraints on the same function that we are trying to map, coming from different subterms of the terms that we are trying to map over. And then if we have more if we have deeper specifications, sometimes we can end up with a constraint of the form f needs to be of the form terms g for some g. And it doesn't really make any sense because terms doesn't take any function as input. So what does it mean? Well, it just means that our algorithm actually is working with formal functions, about functions, with function expression, if you want, and not with actual functions. That's just a subtleties that you can see in the paper. It has to do with true nesting that we don't have in that terms just GADT. And there is a further complication, which is that sometimes we need to perform unification in the middle of the algorithm to be able to know what are the constraints that we want to entail. And so there is a proof of concept implementation in AGDA at that address. We chose AGDA not for verification purposes because this is not verified. We just chose AGDA because it's good to play with formal grammars. And thank you for your attention.
We can take one quick question.
No, probably someone else.
Oh, okay.
I can. Yeah.
Thank you for the nice talk. Have you given any thought to contravariant functors? So if you had like a function type in your specification there, or something like that?
So yes, we have given thought to that, and we decided not to take them into account. So yeah, so in the definition of a GADT, let me go back to what was this slide. There, for example, all the arguments need to be positive in some sense. So contravariant constructor should not be allowed. And so, for example, in the implementation that we have, we don't even have function types to avoid that. Yeah.
All right, let's thank the speaker again.
Thank you.